Action! Okay, so this robot has 3 different parts to program. You have the Raspberry Pi, which is it's a computer, so you have to SSH into it, secure shell, and then program it with Python. The RC car pretty much is ran by the Seeeduino. It's a microcontroller. You think of like Arduino. That has to be programmed by the Arduino IDE. Install the board through the settings, like the JSON list, all that. This video is not about that. This video is beyond that. Then there's also the ESP01, which you have to program. That's an espressive chip. You have to install the ESP8266 library for that. Also programmed through the Arduino. So there's 3 things you gotta set up. The Seeeduino talks to the ESP01, then the ESP01 talks to the Raspberry Pi through wireless, like Wi-Fi. They're both on the same network, your local Wi-Fi. For the ESP01, you need a programmer for it, and actually, sorry, I'm freaking holding this light with my hand. I lost my little USB thing, but you buy this USB programmer that you pop it in, so thankfully I had this little serial programmer thing. So I just looked up a wiring thing online on how to program this using this, so that worked out. Otherwise I'd have to buy one and wait for it. The other thing I want to point out, when you're working with the Raspberry Pi secure shell, when you first get that set up, you'll have to figure out the IP address, and if you have it headless and it auto connects to the Wi-Fi, you can scan your network for the connected devices, and you can see here, like it says Raspberry Pi, Raspberry Pi. I have quite a few Raspberry Pis doing whatever, so that's the idea. It would pop up. You could also just plug it into a monitor, and you'll see like a basic terminal like this, and you type in like ifconfig or whatever and find the IP that way. But you need that to SSH into it. But again, this video is assuming that you already are past that. This is like the high level software part. Okay, so I am importing a lot of stuff from the old code just because I had to figure out how to make this stuff work a long time ago, but what I've got is just the basics. So I mentioned before we're using PIO to control the servos, and I'm gonna I did rename this to ChiselBot at one point, just because it got annoying typing all this stuff out. Okay. The other thing is you can't mount the Pi02 in VS Code, like it doesn't have enough RAM. So I'll be working through like SFTP, that kind of thing. Although here I'm just gonna directly edit the files. So go here. I'll do from servo import servo servo equals servo, which this isn't gonna do anything right now, but oh man, it's slow. And then if you look at servo, that's the code right there. I'm gonna manually dial this in because when I dropped it, the this centerpiece like popped out of the bearings, and yeah, now it's no longer centered. Also, I broke the wheel off and moved it backwards so that I didn't have to add like a heavy weight, because this thing is top heavy. But I moved the wheel further back. It makes it like longer, but I didn't have to add like an extra weight to make it back heavy. Alright, so God, that lag. Alright, go to servo, edit this file. Oh yeah, boot center. Oh yeah. So I'll just set the tilt and pan centers to 1500. That's what it says. This could be bad because the motions. This thing can't move that much because like the battery will run into the ground. It can tilt down more than up, which is good because it needs to look down more than up. But yeah, so let's see. Oh my god, this lag. I'm not gonna do this. I'm gonna work out of the editor and use Git. Or actually I'll use SFTP, but yeah. So that these values here will be set here when this method is called. I already saved it. I'll back out, go back to main. We import the servo. I'll just call boot center. There's also there's a boot script that runs and it turns off this LED, like pulls it down, and it turns on the servos, like sets their positions. But you can see right now it's not on, so I turn that off. That way this code isn't fighting the boot script that's running in the background. Now I should be able to run this, and these servos will move. Crap. Let me figure that out real quick. Oh yeah, let me do something real quick. I'm gonna add. Yes, it doesn't track those. Ah, dang it, hold on. Yeah, that's right. Star. There we go. Alright, back here. Oh, no, not there. Let's say from servo.servo folder file and class name. And let's see how bad this is. What happened? Let's see, run. Oh yeah, right there. I see. Yeah, it runs this shell file. Okay, I will do that. Yeah, and it has to run through sudo. Alright, so now it'll work. Okay, so you see it tilted up. I'll dial it in. Oh man, this is gonna suck. Let's see, it went left, or let's do the, I don't know which direction it's gonna go. Let's see, servo center, tilt pan, we want tilt. Let's reduce it by, I saw this number somewhere, 1300. Alright, that's like parallel with this plane here, so it's looking upwards. I'm trying to set it where it's level with the horizon. 1250. That's still looking upwards. Okay, so I did go ahead and bring in all the sensor code. Initially I tried to, make it pretty and not use the syspath hack, but I still ended up doing it because certain things just wouldn't work. And yeah, this is library code. Like, I didn't make this, so there's like so much in here. But yeah, so that, and then the TFmini is using this code, another library. But the important thing is you make them callable. They start up on their own. So when you look at main here, which I already like wrote this code to test it. I also brought in the LED code, which is basic. That one, you set the GPIO mode. Oh, it's over here. And then, on and off is just high and low. There's a resistor on there that limits the current draw. But yeah, and you'll see when I run this code that it works. But yeah, so narrow sensors, the TFmini, go on there, and this is the class. This is the import stuff to use that library. Set it up, self setup when the robot starts up, and then there's the conversion to like inches. Same for wide sensors, similar. Bring in the library, instantiated. Oh, that's double crap. Take that off. That's the same line, right? Yeah, it is. Okay, I'll take that off. Okay, so then get distance, stop ranging. Yeah, there you go. Centimeter to inches. So if I run that, if you watch the LED, I'm going to turn this light down. Well, there. I run that code. I forgot it has to use Python 3 because that TFmini library is written with Python 3, like these print statements. It uses commas. Anyway, the sensors will go off and the LED will go on, but we can verify that it works. Like if I put my hand in front, where's the tape measure? Do like, how about, that's pretty far. Let's go like 4 inches away. So like right there. I run the code again. 3.5, 5.38. It's not great, but that's, better than 80 and 22. And I think, let's see, which one is which? Forget. What is this? Did I not just commit this? So narrow sensor, what? Yeah. So the narrow one is better like farther away, and the wide one is better for closer because the wide has like a super wide beam, and but you can see that error is already there, so you have to compensate for that. See 7 inches away right here. Run it one more time. 6.24, 9.24. Man, that's not great. I wonder if it's like the target. I use this Mac. Let's see, 7. Yeah, there. Eight and 6.9. That's a lot better. I mean, the narrow one is off by an inch. But yeah. So those are working. So we've addressed the servos and we've addressed the sensors and light. The one that's missing is the IMU, so I'll add that in real quick. Okay, so I brought in the IMU. Again, it's from a library, MPU 9250. We're using a thread because the IMU is like started in the background, parallel, quote unquote. And that just runs and samples itself, and you can pull data from it when you want to. See right here, threading, or thread. And we're only looking at the accelerometer and gyro data because the magnetometer, for one thing, it's inside all this crap, you know, so it's definitely not accurate. The magnetometer is interesting if you ever look at like the Earth and then the magnetic field strength, like 70, 80, 90 or whatever. It's pretty interesting, but I also can't really make sense of it yet. I haven't dug that far into it. But anyway, so yeah, this is the class. These are the values. That's all from the library. Then yeah, so then main, you pull it in, IMU. This is a simple like while true loop, you know, keeps going over and over. There's a 100 millisecond delay. You can see like you start the sensor, it's sampling, and then you can print the data as it gets updated. Now you can see that running here. So the accelerometer is these first three over here, then the gyro is the other side. So it's X, Y, Z, and Z is the gravity axis. You can see it's around 1, which is what you want. And if you like turn it, that value will not be 1 anymore because the force of gravity is like going parallel to that plane, so it's not going to experience force in that axis. But another axis is almost 1, the Y, and then I bring it back, see it go back to around 0. And the roll, if you watch the right 3 values here, roll around the x-axis, I think that's like airplane turning. So you go like this way, then that way. I think that, oh man, what happened? This thing's like network sucks. Probably because there's like a battery attached to the side of the Pi. Maybe it's blocking the Wi-Fi, but yeah, if you turn like left and right, one of those values should be changing. It's not streaming quickly enough to tell, but yeah. But and we will use that for the panning, like left and right. That's about the z-axis, which I think is the last one. If you go this way, then that way, those values like shoot up. And positive and negative is the direction, like clockwise, counterclockwise. Let's see. If you look at the values, oh crap. Yeah, I'll have to look at that to see what the axes are. But yeah, that's how it works. So at this point, all the sensors are addressed on the navigation head. Now we'll move on to the car and the ESP01. So previously we worked on the navigation head part. So one thing that I didn't do yet is the WebSocket piece, which this is a client. It's going to connect to the WebSocket of the ESP01, and it's just a bridge between this and this, the Seeeduino, this little board over here. That's like an Arduino. And the other thing I want to talk about, I took these images. They're mostly for the navigation part. That'll be part 3, but it's important to know like the physical dimensions of your vehicle, and in particular like turning and whatnot. But the other thing about that's relevant to this context is the servo control. Like the Seeeduino will tell the servos to go. The Raspberry Pi will tell the Seeeduino like move 1 inch, and you have to have a function, you know, that says that can take, you know, 1 as a parameter and move the robot an inch, which that's not factoring in slippage. You could have a control thing that takes the IMU acceleration and calculates, you know, displacement. But even that, I mean, we're working with like crap parts here, you know. The accuracy is like really bad. But yeah, so that's what's in mind as a top view. Again, with the whole dimension thing, which I'll cover this more on the navigation part, it's like when this robot rotates, it turns about this center, and then this thing swings outwards, this swings outwards, you know. I'll do a visual in a CAD program, like the total like rotational volume or whatever. That's just to be aware, like if you're navigating through a bunch of stuff. I actually have another picture I should pull up. Yeah, so here, like, this is the kind of environment this robot will operate in. They'll just be like random crap, you know. And even if you like segment this, like, we're not working with like a point cloud with exact dimensions or anything. It's really crude. And actually I was thinking about it too. Since this thing will like pan, and then there's like a idea of the beams, I'll just do like I don't know if it's part of the panorama process or a pre-scan, but it will you know, probe the environment with those depth sensors and use that as like a base. So you can immediately tell if the ground is clear or not. You know, like if there's like a crevice or like a drop off or something. That's not really a concern in my application, but you could consider that. But anyway, we're gonna do all that in these 2 folders here. And again, I'm gonna pull some code that's already been written just because it'll save time in the video. But I'll go over, you know, how it works. Then the WebSocket, it'll work with the web client or the Raspberry Pi, you know, like a Python client. So that'll be a way to verify that it's working. Okay, so I'm just doing a quick check-in. I got the socket server for the ESP01 code flashed on there. If you look at the, like, these are the 3 main functions in there. You got a state variable, like client is active, because this does like a looping thing where it's like waiting for a connection. And most like microcontrollers, or I don't want to say most, but like a lot of, like in Arduino, this is a common default programming structure. Like there's a setup and then there's a loop. This loop is it keeps running over and over. Here, like clock speed, that's like the how fast it can run. I don't want to say 1-to-1, but yeah. And you have like an 800 megahertz processor, like it's insane. The cheap like Arduino Nanos are usually like 8, but this ESP01 is 80, which is pretty crazy. But anyway, the point is, this thing keeps looping, right? You see the client is not active, so that code will execute. And here, this is a trivial connect to Wi-Fi thing too. Import the Wi-Fi library here. Connect to your network and password. And then, yeah, this is all. And then it is like a server, this socket 80. Well, most web servers listen to port 80, but this WebSocket listens on 80. There's no web server on this ESP01. So then the baud rate is set up there. You call this function, calls that. This runs first, setup, calls that one. Then this looping is happening, which here is waiting for a connection. And if there is a connection, which, yeah, I remember I had problems with this library code. And I did eventually get it to work, but it was just sus. Like, it doesn't make sense how it works, but yeah. And you see the, like, 1 second poll, it's waiting, or it keeps trying to get data. And then, so the client's available, like, something connected to it, it waits for a message to come in. There's a message, it prints it to the serial, which the Seeeduino, its serial is connected to the ESP01 serial, so that's how it can transfer data between the two devices. Yeah, and then this part I'm not sure. I think it's just flushing the buffer. But the communication is one directional right now. You're just sending commands into the Seeeduino. The Seeeduino isn't sending anything out at this time, but you could. Like the WebSocket is bidirectional. So that's the code for the SP01. You know, it gets the message, dumps it to serial, repeats. And then this is the basic test website, which I forgot the Raspberry Pi has its own socket server too, where you can directly control the Raspberry Pi, which actually is probably what you'd want to do anyway, because the Raspberry Pi socket server is faster than the ESP01. Well, you could send more data. You don't have to worry about like the buffer or whatever, because that's handled for you, and you have more power and all that. So this is the basic code. You can see this is JavaScript. This was C++. So you got your function here, connect. This is a WebSocket. That's the port, or the IP, local IP, the 192. You don't have to put a port 80 on there because it's like assumed. You can put other ports on there like 3000 or whatever. So then yeah, you connect to it, you wait for the open, and then you can talk to it. So as you can see, like here, I've got the ESP01 connected to this computer, and then it's selected, and then this is the actual serial output of the ESP01. This is like what the Seeeduino would read, but anyway, we can test the that is working here. So this code, like if you look at it, you see it's bringing that code in, and so it's running. So you refresh this page, you'll see that. That's the console log. If you look at the network tab, see the message. This sent it outwards. I think down is red. It's downward arrow, like from the ESP01 back to the client, or back to the JavaScript, this website. So yeah. And then if you look here, now you have two YOs. There was one before. So yeah, we've achieved our communication goal right there. So the Pi 0 can connect to the ESP01, and then the Seeeduino will receive those commands on serial, and then it can drive the servos. So that'll be the next step. Okay, so I've pulled in some more code. I stripped a lot of the old stuff out, and just to get back to the basics, but first thing is to go over, you know, what's going on is, so there's two servos, you know, left and a right from a top view, and when you want to move forward, you got to make this wheel turn this way, and this distance, you know, say like from here to here, this is part of a like quarter circumference, and you flatten that out, you know, and it becomes like that far. This piece is over here. once it rolls forward, that's how much like ground it travels. So you have to figure out this radius here from, you know, the pi r squared or whatever formulas, 2 pi r, and relate that with the rotational degree that you feed into the servo, which these are continuous rotation servos, and in the past when I was messing around with them, you would feed them like a degree, like servo right 92 or something, and they would just keep spinning until you stop them. So I have to like externally verify that it works like in the real world. So if I say move 5 inches, that's how far it'll go. And again, it's like there's no feedback other than the inertial measurement from the IMU. But and that thing like vibrates back and forth, so it's like really bad. So you are relying on good grip with the ground and hoping that it doesn't spin. Like on this wooden floor here, it would spin, you know, so you have to compensate for that. But anyway, we go back to the code here. The Seeeduino is wired to the ESP, and it pulls in these header files, libraries. They're just like more code, but for a specific purpose. So he pulled those in. The Seeeduino boots up and does this setup, same baud rate, calls functions that are pulled in from these header files, and then the loop happens where it's looking for a command. I'd probably put a delay there, but I don't know. There's like delays everywhere. I guess we could put like 50 or something. But anyway, so then if you look at the ESP01 part, serial 1 means it's the like a serial channel. It's not the same serial that's being used. Oh my god, that car. My car's also loud too, so I can't be talking smack. But yeah, it has its own serial. Like when you plug it into the Arduino, you can see that serial, but the serial 1 is the one that's coming from the ESP, hence the name. Yeah, so when I'm using these strings, that's like Arduino-ish more than C++, I think. But anyway, so you got, this is the setup call right there, pretty much just baud rate. Clear function, so it like flushes buffer. Here it's waiting for the message, like it'll read that buffer and return it if it's available. And then check message, which that fires, I actually don't know where. When does that fire? Probably should happen here, right? So when this runs, it'll set that motion command, which is inherited, you know, the global scope. So this can read it. I don't want to say inherited, but it's available global scope. So you get your ESP message, and the format I'm going with is like move forward 10 means 10 inches, and then stop would just be stop. It seems silly, but yeah. Anyway, and here you can replace any like garbage. I used to have, you know, like hello or weird opening messages, whatever. You can strip those out and just have the pure command that you're looking for, and then clear the serial, and it goes back into looping or delaying. Yeah, and the whole delay thing was, I remember I had problems with that. But anyway, then this is like the business part. Again, this is mostly like dumb commands. The Pi is going to be doing all of the thinking, all the state management. It's just going to tell the wheels to move and how much in terms of distances. But yeah, so you pull in the servo library, and then this is struct. Set the these are nice if you have like a pattern for something, you're just instantiating it. So you put in like the pin on the Seeeduino board. That's where the servo is connected to. And then this is what I was talking about before with the you feed it a degree, like 90, it's not moving, right? If you want it to go, also like the farther away it is, like 100 is faster than 95, you know. So yeah, this is the thing I gotta figure out, the speed and the runtime. There's like a relationship there, so you could make like a function, but you have to define those. And also, I forgot to mention this, like Arduino is generally single threaded. There's no like parallel processing or something. So it's like, you know, it runs top bottom, this before that. So it's like technically like the servos, one moves before the other. That's not a big deal. I'm not trying to point that out. I'm just saying though, you have to think that way. It's not like JavaScript where you can just hop out, async, do something else, come back. Yeah, and then you just kind of globally coordinate stuff like with a for loop. But anyway, so, and then this is just a guard, like to make sure you don't send a double command to the servo. I'm not sure how problematic that is, but I've had problems in the past, like particularly with the legged robots where the gear would just jump to a huge position because it lost track of where it was. And that's not good, like it sounds bad on the gears. But, so yeah, you set them up, attach them, and then these are initial commands. Stop moving, it sets it back to those 90-degree positions. These are just basic guards to avoid the commands. And this is where it takes in those commands. And I decided, since you could say like 100 inches, I'll cap it to 3 digits. And if it's, you know, 10 or 1, like 1 would be 001. I have to experiment with that. Yeah, this is all, I don't know, it's kind of nasty, but whatever. So you receive the commands from the Pi or web interface like this, and you can steer the robot this way. So I'm gonna get this set up and test it, and then I'll do a video showing the actual robot doing it, doing the commands. So right now the Seeeduino is plugged into my computer with the USB right there, and it's on the Arduino IDE. I flashed this code already, and then we're looking at the serial monitor, which, if you see the blinking blue light, it means it's receiving. There's serial monitor information going on. You can see this scrolling upwards. So when I go to the interface here, which is connected to the ESP, see the messages here. If I send 10, you'll see it show up down here. Let's see. Yeah, there. So that's how the commands go all the way from the, well, this is a Websocket web interface, but the Raspberry Pi will have its own interface that talks to the ESP, and then the ESP talks to the Seeeduino. So right now the Seeeduino is what saw that code, and it'll move the servos. So I gotta do that still. Okay, so I've got this working again where I can actually control it. I only have a basic forward command, but I want to show that it's not plugged in, right? ESP and that is powered through this battery, and then the web client here, I believe, is connected. I need to have like a little status, but if I send a command, it'll move forward. When I click this button. Yeah, and there's like a little delay, but yeah, so, and that, if you look at the code, the inches isn't actually used right now. It just moves at some command or fixed. I remember I had to set these values from trial and error because like each servo they don't match the same speed, and the directions are reversed. That's why like one is less than 90 and one's above. The thing I wanted to point out is when you write this, it'll keep turning to that direction. And normally, I think in a non-continuous servo, like the stop will stop it, or the potentiometer. Anyway, you literally have to say like stop moving, and that sets it back to 90, and that's what makes it stop. The little burst of motion is this 150 milliseconds. So that's where I have to translate a command like move 10 inches to actual rotation and make sure it tracks straight. So that's what I'll mess around with, but that's pretty much it for, oh, of course I gotta add rotation, but yeah. And then I'll add the, next I'll add the async IO, well, the WebSocket part to the Raspberry Pi. So then the Raspberry Pi will command it. Also, I'll add the startup script back in that centers this. And yeah, from there we can start working on the navigation. I'll do another video where it's like moving on the ground on a carpet, and that'll show like the commands controlling it, the strings. Seeeduino, this is the main file. It looks like this, imports this stuff. ESP on this didn't really change. It's working as is. I don't have to remove anything. Most of the changes are in here. Oh man, look at that, nasty. But what I wanted to point out, so when you have the servos move for a while, like 10 inches, I discovered that one servo would be faster than the other, and they would be in sync more when you do short bursts, like 5 inches of motion. But the other thing I just wanted to point out is I don't really want to like keep programming these things, because you have to plug the Seeeduino into the computer, the USB. So aside from these, you know, hard-coded things here, there is a raw command option, which I don't have it programmed here, but you feed in a string like this. It says raw command left servo 90 degrees for 10 milliseconds. Each servo has like a runtime, and that'll get run. So the computer and me can in the future just tell it what to do after I figure out how it should behave without having to program it. The Seeeduino is pretty, like, it's fast to program it. It's just boom, it's done. So it's not really a pain, but like having to program, I guess you'd call it like firmware on a microcontroller, is a pain versus just being able to dynamically program it over the web through JavaScript. So yeah, these things are here, but I'm actually just gonna end up using this one once I figure stuff out more. But I just wanted to show, like, so this is a hard-coded thing, and I have like a 10-inch square, and you can see when I run that by the this right here. So RC will come in, ESP will pick it up from the WebSocket that it has. It'll send it here as like a motion command. It'll set that variable. Parse will pick that up right here, and then it'll see RC is in the string, so it'll do raw commands, and then it'll do this 10 by 10 square, and I'll switch to the robot video now when I hit run. Yeah, you can see it, like for some reason turned on the third turn. It turned like really hard. I don't know if it like the grip changed, but you can use the IMU's yaw detection, like of the Z-axis, the gyro, to slow down that wheel and make it go straight. That's more advanced. For the navigation stuff, the harder thing is, you know, localizing, like navigating, measuring things, that kind of thing. But yeah, so there it is. The robot is controllable now, and then it's all just navigation code from this point.